Hello everyone, I'm Henry. I'll present a generic truthful mechanism for combinatorial auctions. First, what are combinatorial auctions? Here's an example. We have 3 agents, 1 through 3, and 5 items numbered 1 through 5. Each agent I has a valuation function vi, which maps every combination of items to a single value, the value of the combination. For example, V1 of the blue item is 2, V1 of the green item is 3, and V1 of the blue and green item is 4. The goal of the mechanism, or the algorithm, is to compute an allocation of items to agents to maximize the social welfare, which is defined to be the total value of the agents. Here, the objective function is the sum of vi of si, subject to the constraint that si form a partition of all items n. In this talk, we focus on truthful and computationally efficient mechanisms for combinatorial auctions. So there are 2 aspects in this problem. There's incentive issues. For example, agent 1 here realizes that instead of its true valuations vi, V1, if he reports 100 times V1, that is, he over-reports his true valuation by a factor of 100, then the optimal solution will be to allocate all items to agent 1, which benefits agent 1, but hurts the actual social welfare. So in general, we need to impose payments in order to align incentives. And one potential solution is to use the VCG mechanism, which is truthful and welfare optimal. But in general, it's hard to compute the VCG solution and the payments, so it's not feasible for our purposes. The other aspect of the problem is computational issues. So here, assuming agents report truthfully, here's what we know. For n valuations, which means vi of s plus vi of t is equal to vi of s union t whenever s and t are disjoint. The exact optimal solution is to allocate each item j to the agent who values j most, and that's clearly possible in polynomial time. And more general is the class of submodular valuation functions, where vi of s plus vi of t is greater than or equal to vi of s union t plus vi of s intersection t. So the problem with these valuation functions is hard to solve exactly, but we can approximate the solution to a e over a minus 1 factor in polynomial time. More general is subadditive valuation functions, where vi of s plus vi of t is greater than or equal to vi of s union t. So we know that these valuation functions make the problem hard to approximate. But if we allow demand queries, there is a true approximation with polynomial computation and demand queries. And demand queries are a pretty intuitive class of queries. So a demand query, given the valuation function v and the price pj for every item j, returns a utility maximizing set of items, which maximizes the value v of s minus the total price of items in s, that is the sum of pj for j in s. We will assume access to demand queries throughout this talk. And finally, for general valuation functions without any restrictions, we know that the problem is always hard to approximate. And now let's come back to truthful and computationally efficient mechanisms. So here's what we know. For complement-free or subadditive valuations, we know that the problem can be solved efficiently if we allow a polylog m approximation ratio. But if items are complementing each other, then the problem is generally hard to solve. And in particular, there's no small o of square root m approximation, even without any computational or incentive restrictions. So the bound is based on communication complexity. The main message of this talk is that we kind of interpolate between the two regimes, and we show that the approximation ratio should somehow depend on the degree of complementarity. So first, let's try to understand the substitutes and complements. On the left, we have substitutes items. So the value of a Coke is 1, the value of a Pepsi is 1, but the total value of a Coke and Pepsi is less than 2 because you can only drink so much at a time. So the point is the marginal value of S given T, defined to be the value of S unit T minus the value of T, is smaller than the value of S alone. And on the right, we have complements. The value of a PC is 1, which is the same as the value of a monitor. But the value of a PC and a monitor is greater than 2 because you can't use a PC or a monitor alone. You have to use them in combination. So the marginal value of S given T is greater than the value of S alone. Now, to measure the degree of complementarity, we use the notion of the superadditive set defined by CTZ19. So for a set T of items, we say that T is superadditive with respect to valuation function Vi if there is a set of items S such that the marginal value of S given T is greater than the marginal value of S given any proper subset of T. So in other words, T maximally complements another set of items S. So given this definition, the superadditive width of a valuation function is just the maximum size of a superadditive set. So this width somehow measures how items complement each other. For example, if Vi is subadditive, then the superadditive width D is precisely 0. And we know that for general Vi, the superadditive width D is always upper bounded by m minus 1. So given the definition of the superadditive width, we present a efficient mechanism whose approximation ratio is the smaller one between D plus 1 and square root of m up to a polylog factor for valuation functions with superadditive width D. Now let's look at the mechanism. So recall that the input is n agents, m items, and a valuation function Vi for each agent I. And moreover, the mechanism can only interact with Vi truthfully. And we further make the assumption that the optimal welfare opt is between 1 and m. So we have a very rough estimate of the optimal welfare. And also this assumption is without loss of generality. We can easily remove that, but I'll not go into details here. The idea of the mechanism is to use the framework by Dobzhinsky et al. Of price guessing. So the rough idea is to post a random price for each item and let agents buy utility maximizing bundles as given by demand queries. And here's the mechanism. First, we draw a price P from the set of prices, capital P, uniformly at random. And capital P is all prices between 1 over 4m and m, where consecutive prices are separated exactly by a factor of 2. And also, we let the set of active items A be the set of all items. And then we go to the agents. For each agent I, we make a demand query to the valuation function Vi with items in A and post prices Pj equal to P for every item J in A. And then we let Si be the demand set returned by the demand query. Then we allocate Si to agent I and charge payment equal to the total price of items in Si, which is P times the size of Si. And then we remove items in Si from the set of active items. And that's it. So to understand the mechanism better, let's see an example. Again, we have 3 agents and 5 items. Every item is active at the beginning, and let's say the price we draw is P equal to 1/2. Now we go to agent 1. We make a demand query to V1, which returns S1 equal to 1 and 4. So we allocate items 1 and 4 to agent 1, and we charge price or payment 2P, which is equal to 1. Then we go to agent 2. We make a demand query to V2, which returns S2 equal to 5. So we allocate item 5 to agent 2, and we charge payment P equal to 0.5. Then we go to agent 3, make a demand query to V3, which returns S3 equal to 3. We allocate item 3 to agent 3, we charge payment P equal to 0.5. And the mechanism terminates because we have dealt with every agent, and item 2 remains unallocated. So there are some useful observations from this procedure. First, it's computationally efficient because the only computational costs are from guessing one single price and making one demand query per agent. And also the mechanism is truthful because first, the price doesn't depend on valuations, so no matter what agents report, they cannot affect the price. And second, the allocation and payment are utility maximizing. They perfectly align with the demand query. So there's no reason for agents to lie because we are maximizing their utility for them. Now let's move on to the approximation ratio. Here's the plan. We proceed by 4 steps. First, we show that the mechanism is d polylog m approximate for a simple class of valuations, where each of some disjoint bundles of size OD as a whole contributes value. Then we show that if a class of valuations V is better approximated by another class V prime, and we have an alpha approximate maximum for V prime, then we have an alpha times beta approximate maximum for V. This holds only for some maxims, not all. And the third step is that as a result from CTZ19, it says valuations with superadded with D are polylog M approximated by the above simple class of valuations. And finally, we put the previous 3 steps together. It immediately gives a D polylog M approximate maximum for superadded with D. Now, first, let's see how step 1 works. The simple class we consider as constraint homogeneous valuations. Vi as constraint homogeneous with maximum size D if there exist disjoint bundles of items B1 through BT, where each of the bundles has size at most D, and a single non-negative value per item Q, such that for any set S of items, Vi of S is the sum of Q times the size of Bk for every K completely contained in S. Well, for every Bk contained in S. So let's see some examples. Here's one constraint homogeneous valuation with maximum bundle size 3. Every color stands for a bundle. Now let's look at the highlighted items and consider their value. So for example, T1 here with 3 items has value 3 because it's precisely the blue bundle of size 3. T2 with 4 items has value 2 because it covers the pink bundle completely, but not the red bundle. It intersects with the red bundle, but does not cover the red bundle. So the value of T2 is 1 times 2 equal to 2. And T3 with 4 items has value 3 because the green and yellow bundles are contained in T3, but not the blue bundle. So given this definition, let's focus on one agent and the set of items allocated to agent I in the optimal allocation. So here, let opt I be those items allocated to I in the optimal allocation. These are the highlighted items in the figure. And D is the size of the largest bundle, and Qi is highest value per item. The first observation we make is that partial bundles can be removed because they contribute nothing to the value. So we remove the blue item here from opt I. And then the second observation is that if Qi is smaller than 1 over 2m, then we can ignore agent I and items in opt I because all such items contribute at most opt over 2 to the optimal welfare. And even if we remove these agents and items, the remaining agents still contribute at least half of opt, which is enough for our bound. So then we assume that Qi is between 1 over 2m and m. And the price we post, P, is about half of Qi with probability 1 over log m. So the claim we make here is that whenever P is about half of Qi, the revenue from items in opt I plus the surplus of agent I is at least Vi of opt I divided by D. So it's the share of agent I in the optimal welfare divided by D. So here's the argument. Let sold I be the items already sold to other agents before we query agent I. These are marked by crosses. So the revenue from items in opt I is lower bounded by the revenue from items in sold I, which is in turn lower bounded by Qi times the size of sold I divided by 2. As for the surplus, it's lower bounded by the utility of buying opt I minus sold I because it's a valid choice for agent I to make. Right? And the utility of buying opt I minus sold I is Vi of opt I minus sold I minus P times the size of opt I minus sold I. And it turns out this thing is lower bounded by Qi times opt I minus D times sold I divided by 2. Then we put the two bounds together, and that gives us that the revenue from items in opt I plus the surplus of agent I is at least Vi of opt I divided by D, which is what we want. So the first step is okay. Now we briefly look at the second step. So we say that evaluation function V is beta pointwise approximated by V prime for beta greater than or equal to 1 at S if the value of V of S is not too much larger than V prime of S. It's at most larger by a factor of beta. And for any subset T of S, V prime of T is no larger than V of T. So V prime is dominated by V. And also we say that a class of valuations script V is beta pointwise approximated by V prime if every member of V is beta approximated by some member of V prime. So the key claim we make is that pointwise approximation preserves the revenue surplus decomposition argument. And the reason is the following. First, the revenue depends only on sold I. It has nothing to do with the valuation function. Second, V dominates V prime. So if we replace V prime with V, the surplus does not decrease. And finally, V of opt I is at most larger than V prime of opt I by a factor of beta. So if we replace V prime with V, the benchmark becomes larger by beta at most, and we lose the factor of beta in the approximation ratio. So now we have all three prerequisite steps, and we put them together. That gives the desired D polylog M approximation ratio for valuation functions with superadditive with D. That's all I have. Thanks for your attention. I'll take questions.